Hello everyone. In the beginning of the class, let us see new announcements. Okay. So here and here. Okay. So the only new announcement is May 30th, 2022 class videos uploaded. Hello everyone, I have uploaded the class videos on May 30, 2022 to YouTube. Their URLs are this, and this. Okay. Best regards, Wei Zhen. Okay, let us see the progress of the last class. In the last class, we have taught to chapter 4 slides, page 146, which is unfinished. Okay, let us go to page 146. Okay, please open the slides of chapter 4 and please turn to page 146. Okay, so we were talking about this point. Okay, the maximum Doppler spread FD in the 802.11n model is based on an assumed environmental speed equal to 1.2 kilometers per hour, which implies that FD is equal to 6 and 3 Hz at Fc. Okay, where Fc is the carrier frequency, and Fc is equal to 5.25 and 2.4 gigahertz respectively. Okay, then how do we calculate these two values? Okay, 6 and 3 Hertz. Okay, please look at the blackboard. Because I do not have a blackboard, so I use the Microsoft Word. Okay, instead. Okay, we know that FD is equal to V, where V is equal to the relative speed or velocity between the transmitter and the receiver times Fc and divided by C, where C is the speed of the light. So now V is equal to 1.2 kilometers per hour and Fc is equal to 5.25 gigahertz and C is equal to 3 times 10 to the power of 8 meters per second. So now we need to convert the units. Okay, for the unit of length, we want to convert them to meters, and for the unit of time, we want to convert them to second. So the unit of frequency, we must convert the unit of frequency to Hertz. Okay, so 1.2 kilometers is equal to 1.2 times 1000 meters. And 1 hour is equal to 3600 seconds. Okay, and 5.25 gigahertz is equal to 5.25 times 10 to the power of 9 hertz. Okay, and the denominator remains unchanged. Okay. Okay, then we can try to calculate this equation. Okay, so this is equal to a fraction. Okay, times another fraction. Okay, so we want I want to put the 10 to the power of x in this term, and other numbers in this term. So first 1.2 should be here. Okay. So next 1000 should be here, and it is equal to 10 to the power of 3. Excuse me. And then divided by 3,600. Okay, so I can write 36 here and 100 here. Okay. Okay, and times 5.25. Okay, so it is here. Okay, and times 10 to the power of 9. Okay, here. And 3. Okay, so times 3. Oops. Okay, times. And 10 to the power of 8. Okay, so it is equal to times 10 to the power of 8. Okay, like this. And we can see that here is the meters, here is the meters, and they can be cancelled. And here is the second inverse and second inverse, and they can also be cancelled. So the remaining unit is hertz. Okay, it is reasonable because FD is the Doppler shift of which unit is equal to hertz. Okay. Okay, so next, excuse me. So we can use the calculator, okay, here to find the value of this equation. So first is 1.2 times 5.25 and divided by 36 and divided by 3. Okay, so we have it is approximately 0.058333. Okay, so it's approximately 0.058333. Okay, and times. Okay, so this term we do not need to use a calculator. We can see that the 10 to the power of 3 plus 9 minus 2 minus 8, okay, which is equal to 12 minus 10. So it is equal to 10 to the power of 2. Okay, and the unit is hertz. Okay, please do not forget the unit. Okay, so it is equal to, okay, obviously 5.8333 hertz. Okay, and okay, it is approximately, okay, 6 hertz. Okay, so let me align at the equality sign. Okay, so finally we have found that FD is approximately 6 hertz. Okay, which is the same as the 6 hertz in the slides. Okay, and when FC is equal to 2.4 gigahertz, using the same method, we can find FD is equal to 3 hertz. Okay, which is left to you as an exercise. Okay, so next page. Okay, figure 4.16 shows the Doppler spectrum based on equation 4.35 for 2.4 gigahertz and 5.25 gigahertz. So let us see figure 4.16. Okay. Okay, so figure 4.16 is the Doppler spectrum used in IEEE 802.11n. Okay, the x-axis is F minus Fc from negative 30 Hz to 30 Hz. And the y-axis is the Doppler spectrum from negative 35 dB to 0 dB. And we can see that there are two curves in this figure. The first curve is in dashed line, okay, which represents Fc being equal to 2.5 gigahertz. Okay, this curve. Okay, and the second curve is in solid line, okay, which represents Fc being equal to 5.25 gigahertz. Okay, this curve. Okay, good. Let us go back. Okay, so based on equation 4.35, okay, let us see equation 4.35. Okay, in equation 4.35, okay, the resulting Doppler spectrum has the following form. S of f is equal to 1 over 1 plus a times f minus fc over fd squared. Okay. So the contrast between this indoor spectrum and the Clarke spectrum is dramatic. Okay, let us see the indoor spectrum. Okay, the shape is like a mountain. However, for the Clarke spectrum, okay, in figure 4.15, the shape is like the English letter U. Okay, so they are quite different. Okay, next let us go to a new section, general Doppler power spectrum. In this section, we discuss the Doppler power spectrum in its most general sense and explain how it is related to capital phi c of delta t delta f defined in equation 4.27. Okay, do you remember what is this function? Okay, capital C of delta t delta f. Okay, let us go to equation 4.27. Okay. So in equation 4.27, okay, furthermore, if we assume an uncorrelated channel, then the channel will be WSSUS, okay, that is wide sense stationary uncorrelated scattering, and it can be shown that equation 4.26 reduces to capital phi c of delta t f1 f2 reduces to capital phi c of delta t delta f. Okay, because of the wide sense stationary assumption, so the function phi c only related to the difference of frequencies, but does not related to is not related to f1 and f2. Okay, which is equal to the integral from negative infinity to infinity small phi c of delta t tau times exponential negative j2 pi delta f tau d tau. Okay, where delta f is the difference between the two frequencies f1 and f2. So what is capital phi c and what is small phi c? Okay, let us review it. Okay, so we can see that capital phi c is the autocorrelation function of capital C of Tf. Okay, where capital C of Tf is defined as the Fourier transform of small c of t tau. And the small c of t tau is the impulse response function of the channel. Okay, let me okay, nothing. Okay, let us continue. Okay, so what is a small phi c? Okay, let us go back to previous slides. Okay, small phi c. Okay, let me see. Okay, small phi c of tau is called the multipath intensity profile, the delay power spectrum, or the power delay profile. Okay, so let us go back to page 140. Okay, 9. The general definition of the Doppler power spectrum, which we denote by Sc of V delta F, is as follows. Sc of V delta F is defined as the integral from negative infinity to infinity, capital phi c of delta T delta F times exponential negative j2 pi V delta T d delta T. Okay, so we can see that, okay, Sc of V delta F is the Fourier transform of phi c of delta T delta F. And please note that the Fourier transform is taken on the variable delta T. Okay, if we consider a single transmit frequency, then delta F is equal to 0, and the Doppler spectrum simplifies to capital Sc of V is defined as capital Sc of V, and delta F is equal to 0. Okay, because we consider a single transmit frequency. Okay, so there is no frequency difference, or I should say the frequency difference is equal to 0. Okay, so in the previous equation, that is equation 4.36, we can delete the variable delta F here and the delta F here. Okay, so we know that it is equal to the integral from negative infinity to infinity, capital phi c of delta T times exponential negative j2 pi V delta T d delta T. Okay, so we can know that capital Sc of V is the Fourier transform of capital phi c of delta T. Okay, of course, the Fourier transform is taken on the variable delta T. Okay, where V in this equation, okay, here V is equivalent to F minus Fc in our earlier discussion. Okay, why is V equivalent to F minus Fc? Okay, because we can go to, okay, this figure. This is Doppler spectrum, and the Doppler spectrum is a function of F minus Fc. Okay, and now we know that the Sc, that is Doppler spectrum, has only one variable V. Okay, so V is equivalent to F minus Fc. Okay, so this implies that the Doppler spectrum is the Fourier transform of capital phi c of delta T, which is called the space-time correlation function. Okay, we depict this Fourier transform pair relationship in figure 4.17. Okay, let us see figure 4.17. Okay, So figure 4.17 shows the relationship between the space-time correlation function and the Doppler power spectrum. So in the left-hand side of this figure, it is the space-time correlation function, capital phi c of delta t, okay, which is a function of delta t, that is the time difference. And the width of the space-time correlation function is Tc, which means the coherence time. Okay, we will introduce it later. And the Fourier transform of the space-time correlation function is the Doppler power spectrum, Sc of v, which is a function of v. And please remember that v is equal to f minus fc. Okay, the width of the Doppler power spectrum is Bd, which means the Doppler spread. Okay, so to see that the relationship in equation 4.37, okay, let us see equation 4.37. Okay, this equation, we have seen this equation just about about 5 minutes ago, so I do not plan to explain it again. Okay, equation 4.37 makes sense from an intuitive standpoint. Consider the case where the channel is time invariant. Okay, what does this mean? Okay, under that assumption, there are no dynamics to create Doppler broadening. Okay, because the channel is time invariant, or in other words, the channel is static, not dynamic. Okay, so we should expect the Doppler spectrum to be a delta function. Okay, for a time invariant channel, the frequency response of the channel does not change with time. Okay, so capital phi c of delta t is simply a constant for all values of delta t. Okay, this implies that the Doppler spectrum, capital Sc of v is equal to delta of v, which then implies that Bd, okay, that is the Doppler spread, is equal to 0, as we would expect. Okay, next let us introduce section 4.4.4.2, coherence time, Tc. Okay, the coherence time is the excuse me. Is the maximum time that can elapse between transmitting two identical signals and there still being a high probability that the received signals will be highly correlated. Okay, the word coherence means the same. Okay, so coherence time means that the signal in the time remains the same. Okay, so that is highly correlated. Clearly, if the channel is varying slowly, the coherence time will be large, and vice versa. Okay, because the channel will remain the same or of highly correlated for a long time. Okay, so coherence time will be large. Since slowly varying channels have narrow Doppler spectra, okay, that is small Doppler bandwidths, then the coherence time and the Doppler spread are inversely proportional to one another. Okay, why? Okay, because in the last section we have proved that for a time invariant channel, the Doppler bandwidth or the Doppler spectrum is equal to 0. Okay, so for the slowly okay, it is 25 minutes. Let us take a break.